In this lecture, we'll talk about surface integrals. First, recall that u cross v is equal to the magnitude of u times the magnitude of v times sine theta, where theta is the angle between them, times a unit vector that points in a direction orthogonal to both u and v. Its actual direction is given by the right-hand rule. So if we look at the magnitude of u cross v, which is the magnitude of u times the magnitude of v sine theta, if we put the tails of u and v together with the angle theta between them, as shown in this picture, we see that the magnitude of the cross product is actually the area of this parallelogram. And this is what's going to come into the surface integrals everywhere. So to show this, suppose that we have a smooth parametric surface, RUV, which also can be broken down to its components, XUV, YUV, ZUV. And smoothness means that we'll be able to use linear approximation that will become good as we look closer and closer around the point at which we're linearizing, which we're going to have to do in the integration. R's linear approximation around UV then is dx, dy, dz, is this matrix of partials where you have x in the first row and the partials with respect to u and v in the first and second columns, times these little differentials in du, dv, and then we could rewrite this as the partial of r in u in the first column of that matrix, and the partial of r with respect to v in the second column of that matrix, dot these little differentials. So this linear approximation shows us how to go from differentials in uv to differentials in x, y, z. It also creates a parallelogram in space. The sides of this parallelogram is rv, the partial derivative in v of r, the position vector, dv, and ru, du. And so the area of that is a little piece of the area of this surface, more particularly of the linear approximation of the surface, which is moving around the surface, as shown in this picture. And so the infinitesimal area of this parallelogram is ds is equal to the magnitude of ru du cross rv dv, which is simply just ru cross rv du dv. And denoting dA as du dv, we get ds is equal to ru cross rv dA. This Ru cross Rv accounts for the local slanting, contracting, and expanding that R does. So as it moves around, it changes direction. This plane changes orientation, and it changes size, and it becomes of different shapes while retaining the parallelogram nature. And it's through this way that we define the surface integral of a function. So suppose that S, the surface, is parameterized by R, with parameter space being D, and F is a continuous real-valued function of x, y, and z, whose domain includes S. Then the surface integral of F on S is the surface integral of F xyz ds is equal to the regular double integral over d, the parameter space, of f of ruv times the magnitude of this cross product, ru cross rv dA. Let's take an example. So suppose our surface is given in this very simple way. So it's explicit in z. Then we can just take u equal to x and v equal to y, and we find that our position r is xi plus yj plus gxyk. And this means in particular that the partial derivative in x is just I plus the partial derivative in g with respect to x times k. And similarly, the partial derivative in y of r is just j plus gyk. And so we can write out then the differential of surface area, which we know now is given by the magnitude of the cross product of rx cross ry times dA. And we write that as the magnitude of the symbolic determinant as normal for the cross product dA. We do this determinant and we find that the magnitude of that determinant is the square root of gx squared plus gy squared plus 1. So ds is this square root function times dA. And our surface integral becomes the integral over the parameter domain of fxy gxy times this multiplicative factor, the square root of gx squared plus gy squared plus 1 dA. Let's take another important example, that of polar coordinates. So suppose that boldface r is parameterized in terms of little r and theta for r and theta in some polar parameter domain dp. Then r is equal to xr theta, the standard description of x in polar coordinates, r cos theta, I, plus yr theta j plus kr theta k. And rr then, taking derivatives in r, gives us that the first component of the derivative rr is xr, the second component is yr, and the third component is zr. And likewise, r theta is x theta, the partial derivative of x with respect to theta, I plus y theta j plus z theta k. And then we can write our surface integral for polar coordinates as the integral from 0 to 2 pi, the integral over all r, 1 dp r theta times f r theta times this cross product magnitude rr cross r theta dr d theta. So notice here the derivative of area was just dr d theta. There's no r dr d theta. Well, it will turn out that that missing r is already in this factor, the magnitude of rr cross r theta. And so we can't include that twice. And you can just think of this, that we're integrating over r theta parameter space. It's not as really polar coordinates for these two reasons. Now, just to give you an example of the fact that this r in the r dr d theta really is there, take the normal case where x is equal to r cos theta, y is equal to r sine theta, and z is equal to 0. And then the magnitude of the cross products of the partials is then the magnitude of the symbolic determinant ijk cos theta sine theta 0 minus r sine theta r cos theta 0. And that easily works out to this missing r. So we can discuss the properties of this surface integral that we just came up with. So the first important property is it actually doesn't depend on the parameterization chosen, as long as it's a legitimate one. So if we had used r theta, or we had used x, y, or if we had used uv, as long as it's a proper parameterization, this boldface r of the surface. And so when we let those parameters evolve over parameter space and look at the image of r of those parameters, we get the surface. Also, if we're just doing the surface integral over an indicator function, 1d, then we get the area of d. So d would be a subset of the surface, like a subsurface for any d which is contained in the surface. Any has to be taken in quotes yet, because there are mathematical questions that we would deal with in later courses. The disjoint sum property continues to hold, which says that if we're finding the surface integral of a disjoint union of surfaces, say S1 and S2, where S1 and S2 do not intersect, then we can write that as the surface integral over the first surface S1 f ds plus the surface integral over the second one S2 f ds. And linearity, which is now about the functions, also holds, and it says the surface integral of a linear combination is the linear combinations of the surface integrals. So here in this last property, the surface is fixed. So it's one script s on both the left and right sides. A couple of applications of the surface integral. So the first one is if we have in place of f some mass density rho, then the surface integral rho ds is the mass of this surface. So it's the mass of S. The center of mass x bar, y bar, z bar can also then be obtained as, for example, x bar is 1 over the mass of the whole surface times the first moment about the yz plane, which is computed as the surface integral of x rho xyz ds, d surface area. So it's natural at this point to ask, well, what would happen if we wanted to integrate a vector field instead of a function? And to be able to discuss this, we need to have the concept of oriented surface. So a smooth surface will have a unique tangent plane at any point. To see this, we can fix that point and then find two other points on the surface that forms a triangle, and note that there's a unique plane passing through that triangle, which could be thought of as a secant plane, and then let those two new pick points converge to the point of interest, and the plane, which is the secant plane, will converge to this tangent plane. And this tangent plane has an orientation that can be equated to its normal, or rather one of its two normals, because if it has one normal, then the vector pointing in 180 degrees opposite direction is also a normal. Call these two normals n and minus n. And so surfaces are orientable if whenever you smoothly move a normal around the surface, returning to the same point, you will have the same direction as you started. So to see that this is not always possible, think of this following Mobius strip. So start with the normal on, say, the lower right here, pointing outwards. And then if you go around, move around in the back, towards the back, it's still pointing outwards. And then it starts pointing down. And then as you move around to the front again, it's pointing inwards. And you could reach that same point where you were starting outwards and you wound up inwards. And so we think of this surface as having a twist, or in other words, just having one long side. So it's not two-sided. It only has one side, because you can move from something that looks like it's on one side to the other side without ever going across an edge. So the orientation is defined in a couple ways. So first of all, if S is the boundary of a solid, so like the surface of a sphere, for example, then the normal n or minus n, which points outward, so the one of those two which points outward, is called positive at each point, or simply outward. So if the surface S, script S, is given in parameterized form as follows, r uv, where uv are in parameter space, and the surface is smooth, orientable, parameterized surface, then the positive unit normal is this one, the one that's defined as n is equal to ru cross rv over the magnitude of ru cross rv. And this normal must satisfy the following properties. So n, which is ABC, must be given by A is the cosine of the angle between n and I. B is the cosine of the angle between n and j. J is this unit vector in the y-axis direction. And C is cosine of the angle between n and k. To see this, we just write, say, the dot product corresponding to the first one in two different ways. So n dot I, well, n is ABC, and dot I then just gives you the first component A. And so n dot I is A. But then using our knowledge of the dot product and how it's defined, n dot I is also the magnitude of n times the magnitude of I, both of which are unit vectors, so that's just one, cosine the angle between n and I. So that establishes the relationship that we need. Now, very often we won't worry so much about the positive unit normal. Instead, we'll say we want n that points upwards or inwards or outwards. So n that points upwards or positive in the z direction is the normal such that c is greater than 0, meaning the angle between n and this unit vector k is between 0 and pi by 2. In other words, when this angle is between pi by 2 and pi, we say it points downwards. And a simple picture would indicate that that just makes sense. We also know that the sum of these components of the unit normal, since it's unit, must satisfy a squared plus b squared plus c squared is equal to 1. But any of them could be negative. We're now in a position to be able to define the surface integral with respect to vector fields. We define the surface integral for vector fields over smooth-oriented surfaces using the dot product, just like we did for path integrals. And we also do it in a way by converting the vector field integral back to the regular function integral using this dot product. So suppose that f is a continuous vector field whose domain includes a smooth-oriented parameterized surface S, which is parameterized by this function R. Then the surface integral of capital F over script S is the integral over S of f dot ds. So this is vector surface field. This is notation, folks. So we haven't really defined this dot boldface S or this dot product, but that's the symbolism for the surface area of this vector field. So this is equal to the surface integral over S of f dot n. This is the desired direction, so usually positive, else upwards. That is given from these tangent planes. And so that will depend on the parameters u and v, because we're taking the partial derivatives with respect to u and v when we form n. So let's call this fuv, and then we do ds, a little increment of surface area. So this integral can be thought of as the amount of flow or flux crossing the surface perpendicularly. So perpendicularly is due to the fact we're dotting it with this normal. So we would choose the normal to be in the one direction or other direction to determine whether we want the flow into, say, a sphere, some type of surface, or out of that surface. Or if we want it through a surface passing from the left to the right or the right to the left. So we choose the normal in that sense to get the answer that we wanted. So this really is two vectors. So the vector field, of course, forms one vector, f, but this ds, which is this new definition, which includes the n in it, so it's kind of like vector surface position. So you can think of it as this n multiplication times a du dv. And so both are vectors, and then you're forming a dot product. So how much they align definitely comes to bear in this integral. The more they align, the more flux there is that you're counting in the integral. So since f dot n is a function, we know how to evaluate it. And so we know that the surface integral of f dot n ds is then, if we define f dot n to be this little f uv, then we're just left with our function surface integral that we discussed at the beginning of this lecture. And we define that as the integral over parameter space of this little fuv of ruv times the magnitude of the cross product forming the parallelogram ru cross rv dA. But then we can bring back the meaning of this little f to write it as capital F of r dot that normal, so ru cross rv over the magnitude of ru cross rv, and then we're left with, from above, the magnitude of ru cross rv dA. Well, these two magnitudes of cross products cancel out, and we're left with the area integral over parameter space d of the vector field capital F at boldface r, the position, in terms of the parameters u and v, dot the cross product ru cross rv dA. Thank you.